I will. I will begin, I suppose. Let me erase this foreign top hat code. Spring by spring. I'll pray. Dear Father, we thank you for today. I thank you again for these students in this class, and just ask that you to be with us, help us to glorify you. We do, Lord. In your name I pray, Lord Jesus. Amen. All right, so I think we talked about the matrix exponential, right? And it had its, definition like this, right? Which, of course, we can write more complete and accurately as sum n equals 0 to infinity of t to the n over n factorial times a to the power n. Great. But I think I need to work out a little theorem. We need to do a calculation. So let's let x and y both be fundamental solution matrices for, let's say, dr dt equals to AR, all right, for a given n by n matrix. All right. So let us think through this. Y is equal to, let's say for the sake of discussion, y1, y2, yn. I'll put vectors on those to emphasize that we're talking about, a vector valued function of time. Each one of these columns is a vector valued function of time. So those are all separately solutions, right? So we have that dy j dt is equal to what? It's equal to a times yj for each j, 1 through n. So these are solutions to the homogeneous problem, right? But X is also a fundamental solution matrix. So we can write X, well, we can write Y, Y1 has to be equal to like X times C1 vector. And because what this is would be like C11 X1 plus C12 X2 C1n xn, right? Where X is, I'm using x1 through xn for the columns of X as well. Why is this true? Well, that goes back to the fundamental theorem. One of our fundamental theorems about n-linear differential equations, which is that if you take a solution to the differential equation, you can express it as a linear combination of a fundamental solution set, right? So I can do this for each one of these. And so I've got of course I've also got, y2 is x times c2, and so forth and so on down the line, right? Yn x times cn. All right. Well, what's this all mean? This means that if I look at y, right, I can write that as, well, y1, y2, yn, right? I'm just writing that down again. But let's replace each one of those with, that's really like x times the first constant vector, x times the second constant vector, x times the nth constant vector, all right? And now is where we need to know a little bit of a really important linear algebra thing, which is the way matrix multiplication works. When you have the same matrix multiplying each column like this, you can factor it out like that. I call this the column by column matrix multiplication rule. And all right, so great. Let's just call this big thing here C for a matrix. It's a matrix, right? And so what we have in summary is that y, which is, by the way, a function of time, is equal to x, which is, by the way, a function of time, times this constant matrix, which is, by the way, not a function of time.
So we can take a matrix out of a matrix?
Well, yeah, these are all square matrices we're talking about here, but the x and the y are possibly a matrix of functions, all right? So, all right, great. How can we characterize this constant matrix C? How about this? What's a time which is usually like, well, any time you want. Let's just put in a time. Say times of t naught, right? X of t naught times that constant matrix. And if we multiply this equation by the is there an inverse matrix for x of t naught? Why or why not? It's a fundamental solution matrix, right? Which means that x of t naught must be invertible, right? So this implies that x of t naught, the inverse of that matrix, times y of t naught has to be equal to the constant matrix. So therefore we have this following theorem, which is that y of t, right, is equal to x of t times what? Well, x of t times x of t naught inverse times y of the initial time. Now you might wonder, who cares, right? Like, what does this matter? Why are you even telling me about this? I know you love to multiply inverse matrices and things, but setting that, aside, who cares? How about this? What if we think about y of t, aw man, piece of trash, y of t equal, the marker, not you guys, e to the, sorry, that was unnecessary, e to the ta, stand by it, aw man, overshot, 5 points. The assist, thank you. Okay. Look at this, and y of t equals e to the ta. If we do that, and we think about t naught equals to 0, then what's y of t naught? 0 times a, right? Also known as e to the 0, also known as identity matrix, right? And so this formula becomes the more useful formula, e to the ta, all right, equals to x of t times x inverse, well, let's say x of times 0, parentheses here, inverse. And that, my friends, is a method to calculate the matrix exponential if you have a fundamental solution matrix. So in the surprise attack mission, I asked you guys to calculate the matrix exponential after you already found the general solution. With this, you can do it. Like, let me make up an example. And I'm going to do it. I'm going to do it without the, I'm not even going to write down the matrix which this is the solution for. Let me just like make up a solution. So suppose you find r of t is like, I don't know, c1 e to the t times 1, 4 plus c2 e to the 3t times, I don't know, 68 and fourth up here, there. All right, great. So in other words, this is like my x1, and this is like my x2. So I can form a fundamental solution matrix here, all right, by e to the t, 4 e to the t, e to the 3t over 4, and 68 e to the 3t. All right? And then we can find, okay, so what's x of 0? E to the 0 is 1. So you get 1, 4, 1/4, and 68. All right, great. So what's the inverse matrix of this? X of 0 inverse. How do you do that? 1 over 1 times 68 minus 4 times 1/4, which is 1. Flip the diagonals. I told you guys about the 2 by 2 inverse formula before, didn't I? When we were starting up the discussion of matrices, I think at the very beginning, in like the first half hour I was talking about matrices, I wrote down ABCD is 1 over AD minus BC. Flip the diagonals, put minuses on the off diagonal. That's the formula for the 2 by 2 inverse. Let me write it out again just in case you didn't know. I guess I'll write it up here. I'm using this formula. ABCD inverse is 1 over AD minus BC. Flip the diagonals. Minuses on the off diagonals. There you go. That's the formula for the 2 by 2 inverse. So, what do you know? 1 over 67. 68 minus 1/4 minus 4, 1. There's my x inverse of 0. And then, so to find the matrix exponential here, we can do it if I had more room to. I'm going to write it over here. So let's see here, my matrix exponential e to the ta, if we believe the general derivation, is supposed to be x of t times x of 0 inverse. I'm going to pull that 1 over 67 out front. My x was e to the t, what was it? 4 e to the t, and then I had e to the 3t over 4 and 68 e to the 3t, right? That times, I pulled the fraction from x inverse out front, but I got 68 minus 1/4 minus 4, 1, right? And so what do we get here? 1 over 67, 68 e to the t minus e to the 3t and then minus 1/4 e to the t plus 1/4 e to the 3t. And let's see here. What's 68 times 4? It's 292? 272? It should be 240 plus 32 is what? I think 272. Correct me if I'm wrong. 272 e to the t. Oh, and there's another. I'm going to factor the 272 out. 272 times e to the t minus e to the 3t, I think. this times that. And then finally, I'll factor the quarter out this time. 1/4 minus e to the t. Oh, wait a minute. There's a 68. Did I miss? No, I didn't. 68 squared. Sorry, I'll get it eventually. So minus e to the t, because this times that. The 4's cancel. And then I get plus 68 e to the 3t. All right, there you go. So that is the matrix exponential for a system if that's the general solution. Now, I probably won't ask you this question. I forgot to move the camera. Oops. Sorry, people not here. There it is. There's what you've been missing. So any questions? I have a question. Which system of differential equations takes this as its solution? Like dr dt equals to ar, what's my a? This isn't a question I usually ask. The question I thought of right off the top of my head. You know, I think I see a way to do it. We remember we worked out the other day, like yesterday. Tuesday doesn't exist, right? So e to the ta was equal to a e to the ta, right? So if we were to differentiate e to the ta, right, and then evaluate at 0, that should give us a. You could do that. I don't want to do it, but just, observation. So now you guys will know how to do the problem I asked differential equations next semester that they can't solve. I can't ask you guys it because I already told you it's no fun, right? I mean, maybe I will. I don't know, but because e to the 0 is the identity, so we just get a. Which in some sense isn't very surprising, right? Because, like, of course the linear term in the expansion, which is essentially a Maclaurin expansion, of course that's going to be the derivative at 0. What else could it be, right? But this stuff is non-commutative, so it might give you pause. All right, let us work out another example having nothing to do with this. Well, I mean, something to do with this, but just easier. I'm going to keep it symbolic. So let me remind you the magic formula, which was what? It is a way of expanding the matrix exponential with respect to an eigenvalue, let's say e to the lambda t. Although this identity here is true even when lambda is not an eigenvalue. It's just that when lambda is not an eigenvalue, the magic doesn't happen. I mean, the formula is still there, but it's not magical. It's just a formula. But when it's an eigenvalue, then there's an eigenbasis, or more generally, a generalized eigenbasis, which means that we can actually calculate those vectors on this sum in such a way that it truncates. All right, so that's just a reminder. So example 2, suppose A is 4 by 4 matrix, and V1, V2, V3, V4 are not equal to 0. And let's suppose they satisfy some conditions. So number 1, let's suppose that a minus 3I times v1 is equal to 0. Let's suppose that a minus 3I times v3 is equal to v1. Let's suppose that a minus 4I times v3 is equal to 0. And number 4, let us suppose that a minus 3I times v4 is equal to v3. All right. So let's do the easy part first. So our goal at the moment is to solve, we would like to solve, what are we trying to do? We're trying to solve dr dt equals to ar, right? Trying to solve the differential equation that has a as its coefficient matrix, okay? This is a 4x4 problem, so we know that there should be 4 solutions, 4 linearly independent solutions. And 2 of those are super easy. We don't really need to do like this one, right? And this one, what do these 2 conditions mean? 1 and 3 are both making v1 and v3 eigenvectors. So 1 and 3, we see eigenvectors. So we can just write it down. R1 of t is what? What's the eigenvalue? 3. So we do e to the 3t times v1. And I'm feeling guilty for not writing vectors on these, so let me fix that. Vector, 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 vector. It wasn't so long ago I took points off in Calc 3 for you not writing vectors. I probably should write it at this point. Don't tell the other students, but I don't write vectors in the higher courses. So there is, as I've called it, an eigensolution. That's one of my fundamental solutions. And also our, let's call it 2 of t is e to the 4t times v3. I'm just going to put those solutions first, just to get them out of the way. My first solution, my second solution. Yes, sir?
How did we get the mean for our eigenvalues?
It's this 3 and this 4.
Yeah, where did those come from?
I gave this. 1, 2, 3, 4 is given.
Oh, those are given?
Yes,
Okay.
given. Like the problem in your surprise attack mission, I just gave you 4 vectors, but I didn't even tell you the matrix. I just told you these kinds of conditions. This one's not quite the same as your problem, but it's also not so far away from it either. All right. So let's try to understand what we should do with the next one. Let's try to process number 2, right? Let's work on number 2 here. In other words, what I want to do is to calculate e to the ta times v3. I'm going to call that my third solution. R3 is equal to that. Right? Now, which we should use the magic formula, right? With lambda equal to what here? 3 or 4? Like, we should obviously use 3, right? Because this one has a 3 in the formula. This is the chain condition I talked about. So we're going to do e to the 3t times I plus t times a minus 3I plus t squared over 2 a minus 3I squared plus da 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 da. All right. So let's work that out. And I'm supposed to multiply by v3, right? So I have e to the 3t times I v3 from my first one, plus t times a minus 3I v3, plus t squared over 2 times a minus 3I times, I'll write it out, a minus 3I times v3, plus higher order stuff I don't care about, all right? So what happens here? We have e to the 3t times v3 plus what? We're given right here, right, that a minus 3I times v3 is equal to, not 0, but v1. So I have v3 plus t times what? Plus t times v1. Then I have plus t squared over 2 times a minus 3I times v1. See, because this right here is v1. But what is a minus 3I times v1? Now you can say what you said. 0, right? That's 0. Ah. And so is all of this, all 0, past that point. So the solution for R3 is simplifies to e to the 3t times v3 plus t times v1. There you go. There's our v3. All right. All right. One more to go. R4, right? Which is going to be e to the ta times v4. Which I'm going to skip a step if you guys don't mind. This is e to the 3t times v4 plus t times a minus 3I v4 plus t squared over 2 times a minus 3I squared times v4. See, I'm just multiplying v4 through the series, all right? Plus 1 over t, come on, t cubed over 6 times a minus 3I cubed times v4 plus dot, dot, dot. So now what happens? The math works out just a little differently, right? So we have e to the 3t times what? Times v4 plus t times, what was that? Oh, that's t times v3? Okay, cool. And then what's this? Plus t squared over 2, a minus 3I times what? Use up one of them to make it into a v3, right? But we still got a copy of, you know, we still got a, copy of the matrix. But look at that. What did we see in the previous calculation? We worked this out already, right? What is a minus 3I? What's a minus 3I squared when it acts on v3? It worked out to 0. So we already know this part works out to 0, right? From our previous calculation. And what does this work out to? That's v1, right? That was given. That's part of the 1, 2, 3, 4. So v4 plus t times v3 plus t squared over 2 times, you said v1? Right. And so what's my general solution? General solution looks like r of t is equal to like c1 e to the 3t v1 plus c2 e to the 4t v3, all right, plus c3 e to the 3t times v3 plus tv1, and then plus c4 e to the 3t times v4 plus tv3 plus t squared over 2 v1, and there you go. That's the general solution here. Two eigensolutions and two generalized eigensolutions. All right. Yes, sir.
Say if in this instance instead of v1 equals 0, and it
If instead of what?
for your given solution or given
The purple part.
up there, yes.
Yeah.
What if there's no zeros?
What if there's no zeros?
Like if the a minus 3i v1 equals
Well, there are other ways of writing that. Like sometimes I change it a little bit so you have to think a bit, right? Like I could trade 1 instead for a times v1 is equal to 3v1. So your job, if I give you something like that, is to understand what it means, right? Like this one, right? We could trade that out for a v4 is equal to 4v4, my bad, 3v4 plus v3. You could do that. See, that's another way of writing that condition.
gotcha.
Uh-huh. But like last class, I defined the chain condition, so I wanted to start with that. But in the surprise attack mission, I might have actually made you like make a step before you got to these. Yeah. But this is differential equations and not linear algebra, so there's probably not too much algebra between the given that I gave you and finding the chain conditions that you can use the magic formula on. All right, so one more example for today. Let us, I may not finish this one today. I'm going to try. We'll see what happens. But let's look at the differential equation. Let's say y prime prime minus 2y prime plus y equals to 0. All right, we're going to let x1 equals to y, x2 equals to y prime. So we have x1 prime equals to x2. We have x2 prime equal to y prime prime, which is also equal to 2y prime minus y, which, by the way, is minus x1 minus 2x2. Lo and behold, x1, x2 prime equal to 0, 1, minus 1, minus 2. x1, y1, x1, x2. You'll forgive me, I have to put it into double speed here since I was so late. Now, I already know this is not going to be a matrix which has enough eigenvectors. Like I know already. So the determinant of minus lambda 1 minus 1 minus 2 minus lambda is lambda plus 2 times lambda plus 1. Oopsie. I did something wrong. You guys got to stop me. Where's my mistake? Minus, plus 2y prime, right? So this was not a minus 2, this was a plus 2 right here. This is a plus 2. And as such, this is a 2 minus lambda, which makes this a lambda minus 2. Lo and behold, lambda squared minus 2 lambda plus 1, which of course is lambda minus 1 squared. Set that equal to 0. My eigenvalue is simply 1, right? So there's just one eigenvalue. It's 1. All right? And as such, oh, by the way, this is A. All right, so A minus I times u1 is minus 1, 1, minus 1, 1 times uv. So I see pretty quickly that I can just make u1 equal to 1, 1. There's my eigenvector. Then I want to solve a minus I times u2 equals to u1, which gives me minus 1, 1, minus 1, 1 times uv equal to 1, 1. So that gives me, like minus u plus v equals to 1. Do you guys, I'm sorry, I forgot to write my 0 over here. Do you guys agree that's an eigenvector? If you go back to the original, matrix A times 1, 1 gives me 1, and then minus 1 plus 2, also known as 1. So A times 1, 1 gives me 1, 1. You can check, it worked, okay? Now I'm looking for a generalized eigenvector of order 2 here. And so I get this, which I might as well let u equals to 0, so v equals to 1. That gives me u2 is 0, 1. So the answer then, r of t, is c1 e to the t times 1, 1 plus c2 e to the t times 1, 1 plus t times 0, 1. Or did I do that wrong? I did that wrong. This one comes first, right? 0, 1, and 1, 1. Yeah. Sorry, I got to be careful. If I don't write out the magic formula, I make mistakes. But if we work through the magic formula with lambda equals to 1, we should get that. Which tells me then that x1, which is equal to y, is actually what? c1 e to the t plus c2 t e to the t. Check it out, yo. The method of generalized eigenvectors is another way to derive multiplication by t for the repeated root case. Now, do I recommend you solve this differential equation like I just did? I certainly do not. Right? This is a constant coefficient repeated root quadratic problem. You should do this in all of 30 seconds, right? You just characteristic equation, factor the thing, write answer down, done. But I wanted to show you that if we convert it by reduction of order to a system, and we find the generalized eigenvector for it, that will bring in the t that we needed before for the repeated root. This is yet another way of understanding where that t comes from. I'm fond of this method, but anyway, I will shut up. Enjoy your break.